hovering with anticipation at the precipice of example 2.c. Right? So we know that example 2 is going to be taking some input for our main function, right? argc and argv. We know we're going to take whatever the first parameter is, the argv of 1. We're going to pass that to a2i, turn that into an actual, like, integer, store it in the integer a, and then pass argc and that a into subroutine. Subroutine is going to do 2x times y, where, the argc turns into the x and the a turns into the y. It's going to do 2x times y, return that, and then it's going to return that back again as well. Thank you. All right, so we're going to get into this and look at it. Okay, so yeah, then we did talked about LEA. We said LEA is the exception to the rule that angle brackets mean go to memory. LEA is just calculate whatever address is inside that form and store it back into EAX. And then, we left off where we said add and subtract. They're as you would expect, but like I talked about before on the board, you just need to know that, if you have like an add ESP8, this does ESP plus 8, and it stores it into ESP, right? So the left-hand side is still the destination, but with these two parameter things like add and subtract, each of those two parameters is, one of the operands, and then the destination is still where it's stored. So ESP plus 8, move it into ESP. Or subtract EAX from EBP times 2. In this form, right at the bottom, we're using an RM32, and I said for everyone except, for everything except LEA, if you see the angle brackets, you're going to memory at that address. So you would take whatever the address is in EBX, well, you take whatever the value is in EBX, multiply it by 2, treat it like an address, and then do EAX minus whatever that memory content was, and then store it in EAX. Yes?
This question wasn't covered earlier today. What are those flags?
Oh, yeah. So you came in a bit late, and actually, no, these weren't covered. So when we were talking about the E flags before, I said the only flags I actually care about you remembering are the sign flag and the 0 flag. These are a bunch of those other ones that I say I don't care about you understanding, but this was just to say that there are all those other flags in E flags which are getting set based on these operations taking place as if they were signed or unsigned, like and unsigned. Like it does it both ways, and it sets the flags equivalently. So it's like the overflow flag, sign flag, 0 flag, auxiliary flag, parity flag, carry flag. You only care about sign flag and 0 flag there. Because basically, when we get into conditional logic, I said that these flags are, you use them for conditional logic. You say, if 0 flag is set, do this, otherwise do that. But I'm just trying to be exhaustive in listing which flags. So when you go to the manual, it'll say, these are all the possible things which can get changed here. So this is just to let you know later on when we have other conditional forms which actually depend on the overflow flag, for instance. It could have gotten set by something like an add instruction or something like that. So yeah, again, no memory to memory kind of things. So you can't have angle brackets on both sides. But this just does EAX minus the contents of memory at EBX times 2, treat it as an address, and then store the results back into EAX. All right, so I'm going to go through this now. So as with last time, green is just some assumed value that this happened to have when we first get to main. I just made up some values for these green values. Red are things which are modified after a given instruction has actually executed. And, we've got our stack over here at our stack pointer right here. So as expected, we see our standard creation of a new stack frame right at the beginning. Push EBP. That's going to save the pointer from to the top of the previous stack frame. So push that on the stack right here, 12FF50 on the stack at 12FF24. And so we just assumed that, EBP happened to be 12FF50 when we started this code. And ESP is red here because, anytime you have a push, you subtract 4 from ESP so that, it's still pointing at the stuff that's on the top of the stack. All right, so that's it for this instruction. This instruction. Oh, and sorry. And then like I showed over there on the on the whiteboard, you know, this is what I'm going to assume the values are for that were on the stack when main was called. So there's the address after call main. That's the saved IP I had on the board. There's the argc, which I'm going to assume is 2, because I'm going to pretend I passed in one value to this. And then there's the argv pointer, which is pointing at an array of pointers to strings. So executed the first instruction, saved our stack frame as normal. Next instruction, again, as usual, we take whatever the stack pointer is pointing right now, which is 12FF24, and we put that into EBP. So EBP is read up here. All right, so that's the only thing that happened this time. Change to register, right? All right, so now here is a very interesting case. This is sort of problematic. I probably should go back and change, well, so I would go back and change this example, but it takes so many slides to update that I'm never ever going to change these examples. So right here, we have a push ECX, and we're tasked with the question of, okay, what's the point of this? So you might think, and you might go back to your notions of call save registers versus call save registers. ECX is a call saved register. Or, you know. The thing is, this turns out not to be a call saved register. Push, anyways. What's happening here, so I said if it's a call, sorry, maybe call east. Someone on the phone? Someone on the, okay, that's just me echoing myself back. Do I need to do that? Nope. So this is why I was going to put them on the board. ECX is a caller saved register, right? So you might think that ECX is being pushed right now because main is going to call subroutine, right? So main is going to be the caller of subroutine, so maybe it's just like pushing its caller saved register at this point. But this is not actually, this turns out not actually to be the case because we know this is not the case because there's no corresponding pop into ECX at the bottom of the code here, right? So if this was a caller save register, we'd see a push at the beginning and a pop at the end, basically. But there's no pop ECX down here in the end of the code. So it turns out this particular push right here is actually Visual Studio's wonky way of allocating space for a single integer local variable, a, in our source code, right? So we knew we had a single variable a. And so what it's doing right now is it's pushing ECX. So it's moving the stack pointer down by 4. And this turns out to actually be just allocating space on the stack for the variable a. For anything greater than like a single variable, it would normally just do ESP minus something to allocate a bunch of stuff all at once. But for whatever reason, Visual Studio thinks that it's going to be faster or more efficient, or maybe actually, since we're not using optimization, maybe it's just simpler, right? So when the compiler's generating it, it may say, if I need space for one variable, I'm just going to, you know, push, you know, something to allocate 4 bytes. So for whatever reason, probably almost certainly due to the fact that we're not optimizing at this time, Visual Studio says, I'm going to go ahead and allocate 4 bytes by just like pushing whatever ECX is right now. You don't care what ECX is right now. What you care is that you move the stack pointer down by 4. And therefore now there's a little slot that you can store values for A. So what I said here was that ECX, oh, so I made these not green anymore, but all these things at the top, the EAX, ECX, EDX, these were all just our initialized values, whatever they happen to be at the beginning. So we did push ECX, and that put hex babe onto the stack, but we don't actually care about the literal value right now. We're actually just allocating space so that there's 4 bytes there that we can store the value for A later on. And like I said, the only way we would really know that at this point is because there's no corresponding pop back at the end as well. So, all right, so we allocate space, and I'm saying over here to the side, okay, well, this is secretly where we're going to put integer A. That's where we're storing, that's, you know, 12FF20 is the address of A, right? So, you know, in your C syntax, you can use the ampersand to get the address of a variable. That would be 12FF20 here, and right now, that variable has never been used, so there's, you know, it's undefined right now. We haven't assigned anything to A yet, right? We never assign anything into A until we call A to I to get the value back from that, and we do assign to A. So right now this is an uninitialized local variable. And ESP changed as well because we did a push. All right. So next instruction, this is why, I wanted you to have the copy of the picture on the board for people out there remote and people here. So next instruction we see, this is our first time we're seeing some RM32 form being used. What we see is EBP plus C. So take the address EBP, add 12 to it, treat that like a memory address, go to memory there, and take whatever's in memory there, put it in EAX. So let's calculate what that's going to be. We see right now that EBP is 12FF24. So 12FF24 plus C, which is 12, we go plus 4, plus 8, plus 12. All right, so that's 12FF30, which you could have also got by just doing 24 plus C is 30. All right, so we get this calculation inside the angle brackets is 12FF30. And so now we want to take whatever's in memory at that location and put that into EAX. So per our assumptions, we just assume that that holds the address 12FFB0 because that's just wherever argv happens to be pointing at the time. So Bill, over to the board. So in our example right now, this would be the 12FFB0, like a literal address. And this right here, so this is what's stored in the value, and this address is 12FF, and was it 30? 30. Right? So we took this value and put it into EAX. That's what this instruction does right here, right? And so why would we want that value? Well, that value is the pointer at this address up there, right? So this address right here is 12FFB0, right? So we grabbed that pointer, which points up to here, and we stuck it in EAX. Now, the thing is, if you remember the C code, right, we're going to be accessing argv of 1, right? So right now, that thing points at the base of this argv array of pointers to strings, right? So right now, we have the base. We have it pointing at argv of 0, but we don't want argv of 0. We want argv of 1. So the next instruction, what does it do? It takes EAX, which is 12FFB0, right? 12FFB0, adds 4 to it, get 12FFB4, and then move that into ECX. So first we calculate 12FFB4. We calculate that address. That's the stuff inside the angle brackets, right? That's EAX plus 4. That address, go to memory at that address and get the value out. And up here, I'm assuming it's, just some arbitrary 12FFD4 or something like that. So 12FFD4. We're saying take that value out of there, put it into the ECX register, right? Calculate an address, go to memory at that address, put it in a register. That's what we got here. And again, it's just somewhere outside of the scope of our stack. And again, all of that that's on the board is all outside of, what I can represent on this picture, right? Well, we got so much space here. So that's what we just executed, right? So the only thing that changed is ECX gets the value at 12FFD4 put into it. And we're saying that's D4. All right, and that now is the address of, that is really argv1, right? And that is at 12FFD4, that's pointing at some string somewhere, specifically the argv of 1 string, right? So if I put in for command line parameter the number 100, I do example 2 space 100, the string 100 is pointed to, it's sitting in memory at address 12FFD4. So that's the address where the byte sequence ending with a null character is based at. So we did that, and now we have the address where there's some string, right? And so what we're going to do, I'm going to save a couple of slides here because we're going to call some function that we're not going to step into, right? So if we're going to call A to I, so the thing you have to know is that, you know, generally speaking, you know, you don't pass around strings on the stack, right? You don't copy all of the bytes for a string on the stack. The string is typically stored, you know, the string may be stored on the stack, something like this, where it's like somewhere up high and brought in by the OS or something. Or the string may be stored in like your global variables or something. So if you just put in like a quotes string inside of your C program, right, you just hard code a string in there, that's going to get stored somewhere in like the global variables. It's like read-only data that should never get changed or anything like that. So the point is we don't usually like, if you're going to pass a parameter to A2I, right, we want to pass in the string argv of 1, right? But we don't pass it, we don't like stick the entire byte sequence of the string on the stack. We just put a pointer to the string onto the stack. And that's why if you look at the definition for A2I, it says, please give me a pointer, right? It says, give me a character pointer which points at your string. And that's exactly what that 12FFD4 is, right? We said this argv of 1 is actually, you know, it's a character pointer, this right here. So this points to then an array of characters. And so we take this value, which is currently stored in ECX, and we push that onto the stack because now we're pushing the parameters for A2I, right? And so we push them left to right, or sorry, right to left. And there's only one parameter, so there's only one thing to push. So we push the parameter for the pointer to the string we want to turn into a number, push it onto the stack. So had I not been, you know, skipping slides, what you would see is you'd see 12FFD4 put onto the stack right here. You'd see a call to A2I. That call would be put on the stack. Actually, I should put this maybe even to this. Right, so the reason I changed that, right, is because the pointer to the string would have went in this first place, FF1C. The saved return address of the instruction after the call would have went here. But then when A2I is done, right, so we don't care what A2I does. We just care that when it's done, it gives us our number back in EAX, right? So it's some external function which we're importing. We don't care how it works. We treat it like a black box. We just say, I pass parameters to you on the stack. You give me back your return value in EAX. So you would have put the pointer to the stack in FF1C. You would have had the automatically saved return address in FF18. And then A2I would return. It would pop that return address off. And then the next thing right here, since this is a cDecl calling convention, that's why we see add ESP plus 4 at the end. That's me cleaning up after that ECX that I pushed onto the stack. Yes?
Would the FF1C be the original push of the ECX, and then 1.8 would be the push of the new value, and 1.4 would be the return address?
No, so almost. So 1C would be the push of the, right, so if you wanted to get into the full stack frame of A2I, 1C would be the ECX that we push right here, right?
But you have a push of ECX above that, too. Remember when you said it was
There's a move ECX above that, this one right here. Oh, sorry, this push ECX right here, that's actually still right here.
Oh, okay, so it's still the
that,
okay, sorry, I was just reading it wrong.
Yep. So that was basically, that's already there. The stack pointer was already pointing at that at the time when we were about to push this next ECX, and that next ECX would have went 1C. And then return address at 1.8, pop off the return address, and then right here, this last instruction is, I as the caller am responsible for cleaning up my stack parameters that I pushed to this thing. Therefore, I add 4 to ESP to functionally nullify that ECX that I just pushed right before the call. Right, so that's my, trying to save a couple of slides here. Treat it as a black box, basically. Pass in parameters, get back something in ECX. Clean up the parameters afterwards, right? And then now, here, I'm going to save some more slides, because it's a lot of slides. All right. So now, what happens immediately, right? So going back to our C code, right, let's remember what we're trying to do here, right? We are at the point right now where we passed in that argv of 1, which is a character pointer. We passed that pointer onto the stack, called argv of 1, or sorry, called A2I. It returned. And now we've got the return value in EAX. We need to assign that return value to A, right? So we've got some local variable space for A, and so we need to take that EAX and get it into A. So that's what we're going to be up to next. Right? So what do we see right here? What we see is we just got done calling A2I. We know, so we see a move taking EAX and putting it into EBP minus 4. Okay, so this is again an RM32 form. We need to calculate what is EBP minus 4. So at this point, EBP is 12FF24. So it points right here. Okay, so EBP minus 4 is 12FF20. And that's that thing that I said before when we did the push ECX. I said secretly this is where we're going to store the A value later, right? And that is where we store it because we took whatever was in EAX, and here I guess I'm saying it's hex 100 rather than decimal 100, but whatever. When we do the example, pass in 256. Whatever. So anyways, we'll say that, hex 100 is returned by A2I in EAX. And then we're just going to put that into memory at the address EBP minus 4, which is 12FF24 minus 4, 12FF20. Put that hex 100 into the memory right there. So that's why it's red right there. This first thing, A, is modified by that. Now, the next thing we see is immediately after that, we go back to memory at EBP minus 4, which is A, and we move that into EDX. And then we push EDX. And so why are we doing this? So, and the reason why we see, after we did the push EDX, that's why we see right here, this 100 right here, because the stack pointer was right here at 12FF20. We did a push, and we pushed that EDX to right here. So the reason why we're doing that is because that's actually going to be the Y, which is passed into our subroutine. Our subroutine takes an X and a Y, right? And so what happened was, we took the return value, put it into the memory location for the local variable A. And then immediately afterwards, we were passing that A into the subroutine. And so what it actually did was it just pulled it back out, put it in a register, pushed that register. So go back again, show you the C code. Right, so recall, we assigned this right here. That was just that single instruction, move EAX to EBP minus 4, because EBP minus 4 was the memory address where the local variable A was stored. And now, immediately after that, you're going to start calling sub, right? And you start by calling sub, you pass its parameters from right to left. So first I have to pass A on the stack by pushing A onto the stack. Next I have to pass argc onto the stack by pushing argc onto the stack. And finally I issue the call instruction, right? So it's push, push, call kind of thing here. And so in our sequence of instructions right here, this was the assignment of the return value to A. This was reading the A value and putting it in EDX. And then this was pushing the A value as the, rightmost parameter for sub, because we're going to be calling that next. Right? So therefore, we can assume, if we just pushed one of the parameters, the next thing that we're going to do is push the next one, right? So the next parameter passed into sub. Starting from the right, we pushed A. Now we're going to push argc. So how do we find argc? Well, we start at EBP plus 8. So what's EBP? 12FF24, right here, pointing at your saved stack pointer as always. Plus 8 this time, right? So the local variable was minus 4, and this parameter which was passed into the function is plus 8. So we do 24 plus 4 plus 8 right there. We have the literal value 2, which is the argc value. And so we go to memory at this address, pull out the 2, and stick it in EAX, right? So now EAX is modified to be 2. And the next thing we're going to do is we're going to push that 2 onto the stack, right? Because we need to push argc and pass it in as the next parameter for sub. So next thing, push EAX. You got 2 there, push it, modifies the stack pointer as always. Stack pointer just stays with whoever the last chunk of data is that got pushed. And so therefore, what we see now is on the stack, We have 2, which is argc that's being passed, and x100, which is the a which is being passed, but that a is also the y, and the argc is also the x, right? So once you get into subroutine, subroutine calls those variables x and y, right? But main calls those main passes in argc and a, but inside subroutine, those are the values x and y. So we pushed both of our parameters. We're ready to call the subroutine. So we're going to go ahead and do that, and we're going to call it. And here, I apologize because when I originally did these examples, I disassembled this with IDA, and this ended up being like these relative addresses, right? So the previous thing I said, Windows will generally speaking have addresses in the range of like 40 whatever, 40000. With this IDA thing, this is all relative to like the start of my code essentially. So we're just going to pretend that these are legitimate addresses that you would see in actual program, and therefore, when I call the subroutine, the address of the next instruction gets pushed onto the stack. So if I say the address of call is 2F, then the address of the next instruction is 3.4. So that's why I get this 3.4 on my stack, because we're just saying that's the address of whatever the next instruction is. So I issued the call, and now, I called sub, so we expect that, it's not showing the address here, but we know sub is address 0 on this disassembly. So I expect that my next blue box is going to be at address 0. There it is, and now, again, I think at this point we're starting to get comfortable with the fact that the first 2 instructions of most every function are push EBP, move ESP to EBP, right? Save the old frame pointer, set up your new frame pointer to point at, wherever the stack is right now with a copy of the old one. So what do we expect to happen there? Take whatever EBP was. Oh, because I'm executing both of these instructions, right? So again, with these 2 slides at a time thing, it can be a little confusing, right? But EBP was 12FF24. I pushed that, and then I immediately took ESP and moved it into EBP. And that's why you see 12FF10 there. All right, so now let's get into subroutine, right? So what did subroutine do? It did 2 times x plus y, right? But the interesting thing here is we don't see any like multiply instructions, right? So we had a 2 times something, but we don't have any multiply instructions. And you'll see next, right, that multiply got sucked into an LEA instruction. But anyways, the first thing that it's going to do is we have our x and our y on the stack, right? They're right here. Here's our x, here's our y. Those are passed on the stack. These are the parameters currently. Frame pointer's pointing here, right? 12FF10, frame pointer's pointing there. So what's the first thing that this does? It basically takes those parameters that were passed in and moves them into registers so that it can do that math with them, right? So it's going to do the 2x times y, but it wants the math to be done on registers rather than in memory kind of thing. So what the first thing does is it goes to EBP plus 8. So if EBP is right here at 12FF10, plus 8 is 12FF18. And so that is 2. This is that x that we passed in. So it's going to take that 2 and stick it into EAX, right? So now we know x variable will be in EAX. Second thing is going to be EBP plus C plus 12 instead, right? And that's just going to give us our y variable. So y variable is going to go into ECX. So now, after these 2 instructions are done, we have x in EAX, y. Here I'm saying, it's x104 because it was 100, and 2 times 2, and hex 100, 104. All right, so now it's time for teardown, right? What do we have right before this? We had EBP pointing at 12FF10, and next we're going to do that pop EBP instruction. We're going to take that off of the stack, put it into EBP, and then move the stack pointer up so that we got rid of that value, right? And then, next thing, right, you see we're about to execute a return instruction. We've got an address that we want to return to on the top of the stack, because the stack pointer right now is 12FF14, top of the stack. Probably what I should do is I should probably have the little ESP move on the side there as we go along, but like I said, lots. So execute the return instruction. We popped off that 000034, pop that off into the EIP register, right? And now we expect that the next instruction after this return is going to be the 34 instruction. And then what did this do? This did add ESP plus 8, right? So it did ESP plus 8, and it puts it back into ESP. And so what's the point of this here? Actually, I'm going to call on someone. Brad, what do you think the point of having this add ESP plus 8 is?
Sorry, Zeno, we're trying to catch up. We lost you on the audio.
Oh, okay. Approximately where did you lose me?
That right as you were going into LEA.
Right as I was going into LEA? Okay. All right, so back up here quick. We said that right before the LEA, we're in subroutine. Subroutine is going to do 2x plus y, right? That's what it's trying to do. We've got x and y on the stack, right? So here's our x, here's our y. And so basically it's just going to do EBP plus 8. So EBP points at 12FF10 right now. So this is like this is the top of the stack frame for subroutine. It's pointing there, and then it's going to do EBP plus 8. So if we do 10 plus 8, we get 18. And then that leads us right here. So we're going to go to memory at that location, 12FF18, go to memory, grab the 2, stick it into the EAX register. And similarly, we're going to do EBP plus C, and we'll go to memory, grab the hex 100, stick it into the ECX register. So EAX right now equals your C variable X, and ECX equals your C variable Y. And then when we go into the LEA instruction, it's basically just going to say EAX is my X, so 2 times X plus Y, and I'm going to put that in EAX because remember, the LEA is the exception to the rule that you go to memory when you have angle brackets. So you may have angle brackets, but you just calculate whatever that value is inside the angle brackets, and you take that value and you stick it in EAX. So once we did that,
Can I ask a question real quick?
Return value, the 2, so sub just did return 2 times x plus y, and we have our return value in the return register, EAX, and so now we can go ahead and tear down and get out of this subroutine. So the first thing we do is we pop the EBP, which was the previous saved frame pointer. We go ahead and we pop that into EBP, and so that's now going to point.
Hey, Zeno.
Yeah, go ahead.
On the times 2 in the LEA statement, how does it know what to do with that? How to do that multiplication?
Right. So what it really was the compiler when it was generating. Well, so we know that there's multiple forms of the RM32. So I'll go way back. So when I was talking about, I said there's this specific form where you can, which the compiler can generate, which can have the form base plus index times scale plus displacement. And I said specifically the scale right here, this is this little x right here where I say x can be either 1, 2, 4, or 8. So the only forms of this, this combination you can do involve this multiplication being times 1, times 2, times 4, times 8. Therefore,
okay, I follow.
Okay, yeah. So basically the compiler said, I think, if you're just doing 2 times something plus something else, the compiler was just smart enough to know, hey, I can generate an RM32 form for that, and I won't go to memory with it. I'll just use an LEA in order to do that calculation, but then use LEA, which is the exception to the rule that you don't go to memory for the stuff inside the brackets. So it's basically just the compiler being smart and recognizing that it could represent, this very simple mathematical equation using this very specific form of the RM32 form, basically. And yeah, so the 2 was just basically hard-coded in there by the compiler because it knew that it wanted to do this calculation 2 times x plus y. All right. So now we're tearing down subroutine. We're popping the saved EBP into EBP. And so now that means the stack frame is now 12FF24. It's pointing at this old stack frame. Then we do the return instruction, which is going to pop off this 34 that we have on. We say that's the address of the next instruction that was after the call instruction. So the return address pops that off. That space becomes undefined. And then now we return to this 34. So now, I'll ask you again, why do you think that we're doing this add 8 to ESP at the end of, immediately after this call to the subroutine?
Is it the cleanup section?
Correct. So we're cleaning up those two stack parameters that we passed to the subroutine, right? We passed, argc and a, aka x and y. Right? So we passed two parameters, two 4-byte parameters, that's 8 bytes. So we need to clean it up because this was a CDECL calling convention function, right? So we could have forced it to be standard call if we want. We can go back in and we can change the source code to say this is a standard call thing. And then in that case, the return instruction at the end of the subroutine would have cleaned those up, and you wouldn't have gotten that instruction. But that's neither here nor there. So we correctly cleaned up our stack to get rid of those two parameters that we just passed to subroutine. And now we're back into the teardown phase for the main function. So we're exiting main. We know that so notice that in the sequence of instructions, we don't have anything moving anything into EAX, right? So EAX got set back here in sub, and then we returned to right here. And you can see we're going to return from main before EAX ever gets changed again. And that means whatever sub returned, main is going to return, right? And that's per our source code. Our source code said return sub, and that just means whatever sub returns, main returns. So anyways, we're going to be exiting main, and we need to now start destroying our local variables, destroying, any call save registers, just get rid of the stack frame, and then, get rid of the saved return address. Now, this form right here, so this is an interesting sort of generic way to clean up all of your local variables all at once, right? So this instruction is, you can think of it like destroy all local variables, and it doesn't care how many local variables you have. And why does this work? It's because you're taking and you're saying move EBP, which is pointing at the top of your stack frame, and you're saying put that into ESP. So now I'm saying wherever my stack is, down, however many variables I've put and however far down my stack frame is, just go ahead and move it all the way up to the very top of the stack frame. Everything else below there gets wiped out, right? Because anything below the stack pointer, we don't care about it anymore. It's considered, undefined. We should never touch it, that sort of thing. So we just move EBP to ESP. So ESP is now up here at the same place as EBP. And in this case, we only had one local variable in main anyways, so it's kind of weak. But we just had that A, right? So we had the single variable A, which got pushed with this push ECX, right? And so that would have been right here. That was that hex 100. And so we moved, whatever was in EBP, 12FF24, and we moved that to ESP, thus, undefining everything below 12FF24. So that gets rid of all of our locals. Now, our ESP is at our EBP, right? So therefore, if we do pop EBP, we take a saved EBP and we put it back into EBP. And therefore, now we've taken whatever the saved stack frame was that points at the frame for the guy who called main. We put that back in place. And then, finally, we're going to do the return instruction. I guess I didn't put a slide for it, but we're going to execute the return instruction, and that's going to pop off this address after call main. Question?
So just out of curiosity, looking through this, it looks like that whole series where we've allocated space for A and then stuck A in, looks like it can trivially be optimized out. Am I misreading that, or is this in fact an inefficient implementation?
So the question is, is this an inefficient implementation, right? And so all of our code, right, we turn off, so all of our code by default is the debug build, and the debug build by default has no optimizations turned on. So we want, you know, the simple code, which is very easy to understand. Well, and also we want to see more instructions, because if we optimize, then I wouldn't have much code to show you. So, yes, Ariel's correct that right about here or so, right, we took EBP and we moved it to EAX. And we, oh, sorry, not that. It's, I think it's this,
right there, yeah.
this one right here, right? So we got EAX was the return value from A to I, right? And that was, you know, hex 100, right? And so we took hex 100, put it to memory, and then we immediately grabbed back from memory and put it into EDX. So why couldn't we just put EAX? Why couldn't we just push EAX here, right? And the answer is yes, we could have just pushed EAX right here. It's just because we're asking the compiler, do not optimize. The compiler will have, you know, certain sequences for certain things, right? If it has an assignment statement, A equals B, it's going to say, I'm going to put B into memory at whatever location I've reserved for this local variable. And then, oh, look, I need to use that again, so I better get it out of memory, and I better put it, you know, as a parameter for the next thing. So, yep, absolutely, this is, you know, inefficient code, and, you know, you could hand generate some much better code, or you can turn on optimizations and go back and see what it generates, for instance. I think.
Zeno,
Okay.
I think we had a
Yep.
question from somebody
Question?
online before, and they didn't get
I just had a quick question about, in this example, it's RETN, and in the previous one was RET. Those mean the same thing, right?
No, I'm not hearing anything.
You not hear anything, Zeno? Oh.
Yeah.
But you can hear me all right. We're all coming from the same port. Can you start speaking again? I'm sorry, I didn't catch it.
Zeno, this is Greg.
Looks like it's
in this
Gregory,
example,
and I can't hear you, Greg. Yes.
But you're hearing me. Okay, we're all coming through the same exact headphone port on the computer. I'm sorry.
Okay, so I can see in his chat, right, so in the chat window,
the
is
question that came up in the
return
chat.
n the same as ret? So back in our slides when we covered the return instruction, well, actually, I'm not sure. Clarify that for me. By return, by ret n, do you mean like with, so that could be a different disassembler calling the same instruction by a different name, or do you mean like where n is some number?
I think he was just saying in your different examples.
Oh, do I?
It's
Oh, yeah.
actually on the sheet.
Right, yeah, so, yep,
Probably IDA.
right, yeah, okay, I got it. So that had to do with, yes, the fact that the two mnemonics are the same. This just happens to be because this was, IDA disassembled this, it chose to use RETN, and I guess Visual Studio uses just ret. So, yep, same thing. And when we get into, so you will see more instances of different mnemonics for the same sort of things, actually, especially when we get back to, when we get to Linux later on, you'll see definitely different mnemonics for the same instructions for instructions which would have had the same mnemonics on the Intel syntax side of things. And when we get to the very end and we cover, you know, the byte sequences which actually are behind the scenes, that will be a time when we can start figuring out, you know, for two different disassemblers, is it the same instruction, you know, or not, that sort of thing. So we'll probably have a better way to make that sort of determination in the future. Any other questions on the phone? I mean, this was a fairly, okay. This is a fairly long example, right? So does anyone else have any questions about this? Anyone in the room? All right. Good. All right, so now, let's see. Now we're going to, that's not it, right? So I thought I fixed my slides. Wow. All right. So we're going to go through this quick in Visual Studio, but we're not going to belabor the point since we went over it pretty in depth right now. But just for purposes of getting some more experience, stepping through Visual Studio, watching stuff change. So everyone bring up Visual Studio. And the first thing you're going to do is expand example 2 and find your example 2.c, close the other example. And everyone should see this code. Right-click on example 2 and set as startup project. That's what's necessary, like I said, to have when you're debugging whatever the startup project is, that's the thing which it runs by default. So set that as the startup project. Example 2 should now be bold as compared to, example 1. Example 2 should be bold. All right, set a breakpoint at the beginning of main. And then go ahead and run the debugger. This thing also does it. And if it gives you a message like this, it says, would you like to build it? Click do not show this dialog box again and hit yes. Right. So now it's going to compile it, run it. And does everyone have it stopped at the first breakpoint set on main? Yep. So we set this as the startup project. We click to the right to get this, red breakpoint here. And then you can go start debugging or F5. And then you should be stopped right here. And it may prompt you to say, would you like to compile it first? Click the box, say don't ask me again, and hit yes. So it'll just say compile it and then do it.
Do you want to add command line arguments to it yet?
Oh yeah, good point. Thank you, because I always forget that. Yes, so we need to add command line arguments or else it's going to crash for those of you who may have stepped through already. All right, so go to example 2 and go to properties. All right, so now under this debugging portion right here, command line arguments, I'm going to put in 256 because that's hex 100. And then I'm going to hit OK. So this means that when you run the debugger, it's basically going to be doing example 2 space 256, and 256 is hex 100. All right, so now we run it again, hit F5 or go to debug, start debugging. All right, and so now we can, we can mouse over argc and see that argc is 2. And if we wanted to cheat, we could take argv, go into the watch window, and we could paste in argv of 1 like so. And it's saying that argv of 1 has this particular address, 345B8E, and that points at, that's a character pointer at the string 256. So this was the watch window again. We covered this before just briefly to say you can watch registers, but if you find, so you can either it'll be in one of your tabs or under, let's see, view, other windows, no, debug, windows, watch, and you can create a watch window, and then you can go ahead and put in something like argv of 1, and it'll show you the address and the string. So I'm going to now right-click and go into disassembly mode. And yeah, that watch window wasn't really particularly important. So bring back your registers window, or sorry, memory or registers, whichever way you have it set up. Right, so you want one window which has your memory stuck at ESP, automatically reevaluated, one column, 4 bytes at a time, and then another window which is your register. Oh, and this is the cheaty way. So under once you have your disassembly window up, right-click and turn off show symbol names. That'll be checked by default. And so the reason why we're turning this off is because you can see right now I have this thing that says move dword pointer between brackets it has argv, right? So it's telling you this is argv. But again, for those of you wanting to know, wanting to do malware analysis and things like that, you're not going to have anything telling you argv. They're going to be, EBP plus something, EBP minus something, etc. Right? So to make it a little more realistic and to get, I mean, I really, by the end of this, I want you to be familiar with the notion of something like, you know, local variables are EBP minus something, stack parameters are EBP plus something, right? So just when you see something, if you see something accessing memory at EBP plus something, you got to think that's a parameter which is being passed to this function. When you see EBP minus something, you say that's a local variable which is being used by this function. So that's why I want you to turn off the actual names and stuff so that you can just see this and think of it behind the scenes. What variable was this? So just to go through this at a relatively rapid clip, and again, you can always come back and play through stuff at your own leisurely pace. Here we are at main, the very first instruction. What do we see? We see our normal 2 instructions at the beginning. You know, set up a new stack frame pointer, you know, save the old frame pointer, and then modify the current frame pointer to point at our new beginning of the stack frame. So we're going to push EBP, and what do we see on the top of the stack? 12FFB8, right? That's our EBP right here, 12FFB8. Going to move ESP register into EBP register. So ESP is 12FF68. Going to just put that in EBP. So I step over that, and now I see EBP's in red. EBP is 12FF68. Same thing as ESP. Right? So nothing changed on the stack. Now this is our push ECX. This is our you know, misleading allocation of space for the A variable, right? So we have A, and this push ECX turns out to actually be allocation of space for this local variable. So we step over that. Some junk value gets pushed onto the stack, but we don't care because later on when we assign the return value from A to I to A, then this junk value right here is going to get overwritten. Yes?
So I note that it pops up in the registers window, that funny 12FF74
This right here?
equals.
Yep. Are you asking what that is?
Yeah.
I don't know. Let me see. Let's see. 12FF74 equals.
And that's the value we just pushed onto the stack on the right.
Well, I think, yeah. I'm guessing, let's see, what's EBP? Let's see. I'm pretty sure this is going to be like the next instruction. Like, so 68 plus C gives you C04, so 74. I think what it's saying is like this is the upcoming, so for the instruction we're currently on, this instruction right now, this EBP plus C, I think that's going to be that 12FF74. So it's trying to tell you, hey, you're doing a move instruction, you're asking for the memory at EBP plus C. Yeah, there we go. So see, I selected it, I moused over it, it says EBP plus C is 12FF74. And so it's trying to give you a little heads up. Look, you're going to move 345B10 into EAX next. So it's kind of like a look ahead thing for you to, like if you're stopped at this instruction, right, and you want to know what's going to happen next, this is kind of hinting you into what's going to happen.
And then, isn't the 12FFF74 the memory address of the stack?
It is a memory address on the stack, yep. And so it's just trying to say this is an address on the stack, which equals, this is the literal value stored at that address. And, you know, this move instruction is going to take an address, go to memory, and grab what's in that address and stick it into EAX, right? That's what we have up next, right? We're trying to get this argv of 1 next, right? We had the sequence of things whereby we crawled those pointers in order to find argv of 1. So the first step of doing that was going to EBP plus C, and that was, you know, our argv that was actually pushed as a parameter to main, right? So right now, EBP is 12FF68. It points right here. And so we add 12 to it. So plus 4, plus 8, plus 12, right? And that's 12FF74. And so we're going to go to memory at 12FF74, pull out the value, 3, 4. So, I mean, those values which I put in there, those turn out not to be the actual values from a, you know, Visual Studio thing, but, you know, it's just the equivalent, basically. So, right, this 12FFB0 would have been this 34B10. So anyways, we're going to take this and this is the pointer to the array of pointers to strings. We're going to take that, put it into EAX. So to do that, that goes into EAX, right? And what are we going to do next? We're going to take that value, add 4 to it. So that's why we see down here we got the 345B14. That's 345B10 plus 4. So EAX plus 4 is 345B14. Going to go to memory at that location, and we're going to pull out whatever's there and put it into ECX. So now this thing is hinting us, okay, the memory at that location is 345B8E, and that's going to get moved into ECX. Question?
Are the 34,000 addresses pretty standard for Windows for incoming arguments? Is that another sequence that we should be recognizing?
So the question was, you know, is this 34XXX whatever, is that a sort of standard range that you should be recognizing? I'm going to say yes, but I haven't, actually I myself have not like particularly tried to remember that. So probably it was the better answer, probably, but I don't know for sure. Because the only time I've really ever dug into where the argv and argc stuff come from, I was on Linux. So I never dug into it on Windows, basically. So it's telling us, you know, our hint is telling us we're going to get that value stuck into ECX next. So we're going to execute this instruction. ECX 345B8E, right there. That's in our ECX. Next, we're going to push ECX, right? So what are we doing right now? Now we're starting to push the parameters that we're passing into A2I, right? So we got the actual pointer, which is A2I, right? So we said A2I is, argv is an array of pointers. Argv of 1 is just, you know, a pointer itself. So take that pointer, pass it as the first parameter and only parameter to A2I. That parameter is currently in ECX, so we're going to just do push ECX onto the top of our stack here. So we pushed that, and then now, so here's the thing, right? I could step into this instruction, and later on we're actually going to step into like a memcopy instruction and start kind of reversing what's going on inside of memcopy. But for right now, A2I is a black box as far as I'm concerned. I give it parameters, I get back numbers. Good enough? Use your step over to get over this. Otherwise, you'll go in and it'll start, you know, being off in some library somewhere. So, step over. What changed? So when I did that step over, right, some of my register values are going to change here. EAX changed. EAX is now hex 100, right? That's my 256 decimal. ECX changed. Well, that's because I have no guarantee that ECX won't change when I call something, right? So if I didn't want ECX to change, I should have like pushed it and then popped it back again, right? So ECX is a caller saved register, right? I, as the caller to A2I, need to save it if I don't want it destroyed. So, okay, it destroyed it, but that's fine because I wasn't really holding anything there that I cared about after the call anyways. So, ECX got changed, EDX got changed, that's fine. Those are both caller save registers. And remind me at the next break to write callee and caller save registers on the board so that you can see them quickly. Those changed and the IP changed, right, as expected. So some stuff got smashed, but I don't care. All I care about is I got my EAX back. That's what I wanted. And now I'm going to save that into the memory location int A, right? So, oh, and sorry, before that, I got to clean up my stack, right? I pushed something onto the stack to pass as a parameter. Now, you know, this is cdecal. I got to clean up my parameter that I pushed onto the stack. So this right here, I expect that to go away, and 64 should be the top of the stack next. Do it. 64 is the top of the stack. And now we're ready to actually store the EAX return value into EBP minus 4, which is our A value. And again, just to reiterate, EBP minus something, local variables, EBP plus something, parameters passed in by the function which was calling you, if you take any parameters. So save my hex 100 into memory at EBP minus 4. So if I if I want to see well, okay, I'll let it do it. So EX is hex 100, execute the instruction, and then now we see right here, it happened to be the top of the stack at this point, but it need not necessarily be. If I have lots of different variables, it could be just somewhere up on the stack, somewhere in some blob that can be multiple local variables, something will change. So I only have one local variable, so that's why it's at the top of the stack. That's why this changed. That 64 was the thing where we pushed junk there earlier when we did that push ECX just to allocate space. But now we finally assigned something to this previously uninitialized int A. And now it's hex 100. All right, so now we see intermixed. Okay, what are we going to be doing next? We're going to be calling subroutine with parameters argc and A. And then, we're just going to return whatever it returns. So in order to pass the parameters to it, we have to push the values from right to left. So the first thing we're going to do is push A. And then like Ariel said, we already had A and EAX. We could just push EAX. But because we're not optimizing, it's just doing very simplistic transformations of, the sequence of C instructions, or C syntax kind of things. So what does it do? It goes back to EBP -4, pulls that value out of memory, sticks it into EDX. All right? So EDX, where is it? It's hex 100, but we actually, why didn't I see that go red? I don't know. Anyways, maybe it was already hex 100. So EDX becomes hex 100. And now we're going to just push that onto the stack. Right? So now we have these two hex 100s on the stack. This one is the local variable A. This one is the stack parameter, A, being passed into the subroutine. And now next we're going to do EBP +8. Right? So EBP plus something, Katie, what are we saying we're trying to remember about EBP plus something? What kind of variable is that? Yep, so EBP plus something is a parameter passed to this function. So what is that? That's that that's that argc, right? Argc was passed to main. And so to access argc, we do EBP plus something to get that off the stack. And we're now going to put it into a temporary register and then push that register because we're being inefficient. So put it into EAX. argc is 2. So we get 2 into EAX. Push it. And so now these are our left to right passing of parameters. We have A, and then we have argc pushed onto the stack. Now we're going to execute the call instruction. And so, what's the side effect going to be of this, Amy? Right. Yep. Well, you're going too far. So just the call instruction. But what do I actually expect to see literally on the stack next?
Yes. 1054.
Yep. 401054 is going to be pushed onto the stack because that's the instruction after the call instruction, right? I called over and I stepped over instead of stepped into. Okay, I have to restart. So I thought we were going to set a breakpoint right there. So in disassembly mode, you can set a breakpoint. So I'm going to restart. I'm going to be back at main. I'm going to just go like that. Oh, it's not going to work. I guess it doesn't want to hit my assembly breakpoint when I'm in source mode. All right. Start it again. Go to disassembly. Now I can hit this play. What? Okay, it just doesn't like my assembly breakpoint then. Fine. Be that way. Yeah, I set that. It unset it when I went back to source mode. So I set a breakpoint of this call instruction, hit play. Now it'll go all the way to that instruction so that everything else is exactly the same way it was before. I'm going to step into rather than step over so that I go to the target of that call instruction. And therefore, I see on the stack my 401054. And now this right here, this jump instruction that you see, that's because I forgot to turn off the one option for linking, what is it called, incremental linking. So that's why we turn off those options on things. So this is, because there's this option, incremental linking, they want to be able to modify the code as you go. Again, it does it this way. I'm going to stop it. I'm going to go to my properties. I'm going to go to my linker, my general. I'm going to disable incremental linking. So go to properties for example 2, go to linker, go to incremental linking, and set it to no, because otherwise you'll get that intermediate jump instruction, which is just the thing it does so that it can modify the stuff on the fly. All right, so I did that. Start it up again, go to disassembly, go to that call instruction, set a breakpoint, go to the call instruction, and now this time if I step into, now it should go directly to my target, which is the first instruction of the sub. And now we got our standard function prologue, right? Save the stack frame pointer, save the old frame pointer, set ESP to the new frame pointer basically. So you can step over those, push the EBP, there it is on the stack, and oops, I scrolled up. There we go. And then move ESP to EBP. The only thing that'll change is the registers, right? EBP is now pointing at 12FF54, which is that saved frame pointer. Now we're going to, get our X and our Y into EAX and ECX respectively. Right, so go to memory at EBP plus something. So parameter passed into the subroutine. EBP plus 8 is, you can, unless something is omitting frame pointers, you can always assume that EBP plus 8 is actually the first parameter because plus 4 is that saved return address and plus 8 is going to be that first parameter. So EBP plus 8 is your int X. EBP plus C is your int Y. Put them into registers. Bam, bam. All right, EAX is 2, ECX is hex 100. And then just execute that LEA instruction, which is not going to go to memory. It's just going to do 2 times 2 plus hex 100 and load that into EAX. So when I step over the LEA, I expect EAX to be hex 104. And now, tear it down and exit. So, tear it down. We popped our EBP into the EBP, pop the saved EBP into EBP, and then do the return instruction. Again, sorry, do the return instruction and get rid of that saved return address on the stack. Go back to that address. Right, so I went back to that address, 401034. Clean up my parameters, right? I pushed 2 parameters onto the stack before the call. I got to clean them up afterwards because this is CDECL. And so I'm going to clean them up. And then I'm going to move EVP to ESP to destroy all of my local variables. And then pop EVP, return, and now I'm again in, the function which called main. So, any questions on this quick? I'm going to actually show maybe a quick example of, I'm going to change this to standard call, and you can see how the instructions change slightly. But any questions thus far? Anyone on the phone have any questions? Alrighty, so I'm going to quick change this to standard call. I think this will work if I do it like so. I'm not sure though, we'll see. Okay. So I put in this little thing saying, treat this subroutine sub as standard calling convention. And there'll be different, syntax for how you do this in any different compiler, right? So different compilers, GCC will have a different way. But I kind of threw that in there. Now if I go look at the disassembly, let's see what's different, right? So down here, where we call to the function, right, where we call subroutine, notice there is no adding to the stack pointer immediately afterwards, right? And why can it get away with that? Because at the subroutine, we're using that second form of the return instruction, which says return, pop whatever's on top of the stack, put that in EIP, but the second form is return 8, and so that says pop this off the stack, put it into EIP, and then just, add 8 to the stack pointer immediately afterwards, basically. And so functionally the same, either the callee can do it if it's standard call, or the caller can do it if it's CDECL. So that's again just, if you're, say you're doing Windows reversing or something like that, you'll see that, typical Win32 API, their standard call things, they're always going to end in this return, however many parameters it has times 4. All right, we're going to take a quick 5-minute break, get up, walk around, stay awake, and we'll be back at